Hello, everyone, and welcome to this month's Department of Energy Python Exchange. My name is Cameron Riddell, and I will be your host this evening, afternoon, or morning, depending on the time zone that you live in. As you all may know, our goal is to have Python thrive within the National Lab System and associated research sites. In support of that goal, we are joined today by our guest panelist, Dr. Giordon Stark, who will be sharing his prepared remarks titled Reduce, Reuse, Reinterpret, an end-to-end pipeline for recycling particle physics results. Dr. Giordon Stark is a DEF postdoctoral experimental particle physicist involved with the ATLAS collaboration at the Santa Cruz Institute for Particle Physics at UC Santa Cruz. Giordon is accompanied by his interpreter, Mindy Laney, who will be signing here in the foreground to ensure that everyone can follow along with today's discussion. But before we go into the agenda and introduce all of our panelists, I want to remind everyone about a few key points that we have for these exchanges. This call will be recorded, edited, and posted online. As a consequence, please be conscious of the information in the questions that you may ask to ensure that you're not accidentally sharing anything that's privileged or requires clearance. Additionally, as you all know, we are a growing community and we would like to stay in touch with each of you. If you would like to be kept up to date with our monthly exchanges, please sign up for our mailing list, which you can find on our website, meetup.doepy.org. You can additionally find the recordings of all of our past exchanges on this site, as well as a recording of today's exchange once it has been edited. For those of you who have never joined us for an exchange, I would like to share with you that we break these exchanges down into 4 parts. First, we'll introduce our fantastic lineup of host and guest panelists so that you may all get to know them as well as their respective fields and backgrounds. Second, we'll kick off into a coding activity where we'll ask some very applied questions to our panelists to elicit some practical discussion about best practices in software development and where they fit into the world of an academic or scientific researcher. Third, we'll turn things over to our guest panelist, Giordon, who will share some prepared remarks on Python and how he uses it in his day-to-day work. Then, to wrap up, we have a full discussion about the points brought up by our guest panelists, and we'll open this discussion up to our audience. So if you have questions about our prepared remarks, then this is your time to use the Q&A widget or use the event chat and have your questions be heard. We'd love to have the opportunity to interact with you all, so make sure you submit your questions there. Now, let's go ahead and kick off with our introductions. For each of these introductions, I'll share the name and affiliation, and our panelists will tell you what type of questions that they are here to answer. I'll start by first sharing the website link for our DOEPY site. This is where you can find the recordings of all past and this video once it has been edited. Our host panelists, I'll start things off by introducing myself. Hello again, everyone. My name is Cameron Riddell, and while I'm not affiliated with a specific lab, I do have a background in academic research as I studied cognitive sciences in graduate school. For today's exchange, I would love to discuss any and all questions related to Python as a whole, or specific concepts used in Python, especially pertaining to its vast scientific ecosystem relating to tools such as NumPy, Pandas, and Matplotlib. Moving on to our very first host panelist, we are also joined today by Dan Allen. Dan, I see here that you're at BNL, but can you share with us what is that you do and what types of questions are you here to answer for us today?
Sure. I apologize I don't have video working today, but you can hear me, I hope. My background is in the physical sciences, but I've been in a software role at Brookhaven for about 8 years. And I'm happy to answer questions about building ground-up collaborations across the lab or questions about obscure device controls protocols, if that's it.
I love the use of obscure in there. So if we have some very maybe archaic, but maybe modern, but just nobody uses it, technology will come running to you, Dan. How does that sound?
Thanks, Cameron.
Excellent. Next up, we're also joined by Matt Carbone. Matt, I see here that you're also at BNL. Does that mean that you work with Dan?
That's a great question. Um, Dan, do we work together? I guess we don't as much right now, but we've worked quite a bit together in the past on some
Hmm.
projects.
B&L is a big
So
place, but we like to
yeah,
cooperate.
yeah, absolutely. So anyways, like Dan, I have also have a background in the physical sciences. In fact, we actually did our undergrad at the same place. So my background is in chemical physics. I did a PhD in that, but these days I kind of live at the interface between um, fundamental sciences, software, and everyone's favorite topic, AI. So I guess if you have questions about, machine learning and all that fun stuff, if you have questions on, how a scientist uses software, how a scientist writes good software, I can also help with that.
That is an excellent question, and I think we should have an entire exchange just dedicated to, as a researcher, how and why should I write better software? But we'll save that specific topic for a future one, but I'm sure it will come up multiple times here today. Thanks so much, Matt. We are also joined by Tanny Chavez. Tanny, I see that you're at Lawrence Berkeley National Lab. Can you share with us a little bit about what it is that you would like to answer for our audience today?
Sure. So actually my background is in electrical engineering, but I ended up doing a lot of data analysis and machine learning during my PhD and my postdoc. Currently, I am a computational research scientist at Lawrence Berkeley National Laboratory, mainly involved in the development of data science and machine learning pipelines, with the aim of making these pipelines a bit more accessible to a larger audience that may or may not have experience with ML. So I would love to answer questions related to how can we implement and make machine learning algorithms a bit more accessible to a larger audience.
I think that's a very noble goal. I know in my time when I was even in grad school, but especially before grad school, a lot of the computational analyses I would do, somebody would just hand me a script and say, this is the function that you want. And I wouldn't be able to understand my own results. So it's very nice having people like you around to actually assist researchers with very computationally heavy or very statistically heavy operations. Next up, we are joined by our guest panelist, Dr. Giordon Stark. Now, Dr. Giordon Stark is a postdoc at UC Santa Cruz, specifically at the Santa Cruz Institute for Particle Physics. Giordon, can you tell us a little bit about the questions you would love to hear from our audience?
Yeah, sure. I'll just point out that you're missing an O in mine. But I kind of cover a lot of different topics within physics and also in terms of baking. If you talk about physics, I'm happy to talk about, anything all the way from standard model when I search in particle physics, all the way up to beyond the standard model with new theories. And then in terms of software, I feel like I kind of do quite a lot there. I do things from pipeline CI/CD, talking about, Python bindings. But I've also worked in Fortran, Haskell, functional programming languages, and I also have complaints about Perl, Ruby, Java, and all these other languages just from over the years of working at different experiments. So I'm happy to talk about anything in any particular language you like, your favorite feature, your favorite thing that you hate, such as, for example, I hate Python typing, but I do like the coroutines that exist in Lua, for example.
Excellent. So, Giordon, it sounds like you know a little bit about everything, and I'm very excited to hear what you've prepared for us today, and we'll have a lot of in-depth Python talk. Thank you so much for joining us. All right, with the introductions being done, I feel very confident that our panelists can tackle our coding activity. But before we move on to our coding activity, I wanted to let you, the audience, know that you can become a host panelist too. Please just reach out to us at this email, doepy@dutc.io, and we would love for you to join us behind the scenes and become a panelist for one or even more Python exchanges. This is also true if there's anyone you know who you think would be a great panelist. Please refer them to us or simply email us and CC them. We're more than happy to pick up the conversation wherever you take us to. Now, let's dive into our coding activity. For today's coding activity, we'll be playing a game called The World Doesn't or Does Need Another, and the rules of the game are this. Is it really that bad? You spot something in some code that you're reviewing, and you're getting excuses about it, but is it really that bad? Oftentimes I hear the defense of, oh, it's unPythonic, or it's Pythonic, and I really don't care for those terms. Today we're going to take a deeper dive into some coding practices that may be good or bad, and we'll ask our panelists what their opinions and their thoughts are. So in our first round, we have a very classic Pythonism, or should I say an unclassic Pythonism. Jordan, this might be more sensible if you were using something like R, but from module import star, is it really that bad? I'd love to hear from anyone on the panel. I see a big thumbs down from Matt. Matt, why? Why a thumbs down?
This is as bad as it gets. How do you even know what you're importing? How do you know that you're importing the right, do XYZ function, right? How can your users or anyone around you know that you're using the right function? How does your syntax checker and your linter know you're using the right function? This is just as bad as it gets in terms of writing code that people can't understand, can't easily reference the documentation for. It can cause some pretty nasty actual problems as well. If maybe you import the print statement or something, a print is easy, but maybe you import the, dump statement from two different modules can do very, very different things. Don't do this.
I absolutely agree with you, Matt. One of the examples that I encounter a lot, or I use a lot in teaching, is if I did from math import star, and then on the next line I did from logging import star. Well, if you're not familiar with both of those modules, you might not know that there's a math.log and there's a logging.log. And I can think that we can reason enough, say that if I want to log something in the context of math is very different than logging something to a file. And so I think we have pretty large consensus here that from module import star, just don't do it. It makes the code harder to read, harder to reason about, and harder to figure out where did things even come from in the first place.
I'll defend it.
Oh, yes. Yes.
I type Python all day, and I type fairly quickly. So I always write it out. I import NumPy as NumPy. I don't even import NumPy as NP. But many people do not type for a living. They wield wrenches or do other things for a living. And if they're using Python in an interactive context where the code's not going to be saved, but they're using Python more like a fancy graphing calculator, then I would defend something like from NumPy import star, because you get succinct code that a slower typer can quickly knock out and easily read. You can get yourself into trouble where some the built-in in Python and some in NumPy can do very different things. So it's not something I would ever recommend, but I think it raises an interesting question of what is good interactive disposable code versus what is good Jupyter Notebook or library code that's meant to be read by someone later and maybe saved.
Yeah, I think the interactive and disposable is a big importance there, because I can see something if I do from NumPy import star, right? NumPy has at its base has an absolute value function, ABS. So does Python, and they seem very different in what they, or the same in what they do. But I have run into some weird edge cases or corner cases where you're thinking, okay, this is an integer, right? And it looks just like an integer, it acts just like one, but then you try and pass along some other function that says, oh, I can't handle NumPy int 64 types. And you're like, what? This was a Python integer, I swear. And so I do agree, as long as it's disposable and it works and you just need to run it once, see the output, and you're happy, fine. Anyone else on our panel?
Well, the only thing that I'll mention here very briefly that I think is a little bit worse than this happens all the time in a lot of the code that I have to look at, is people append to the sys path pretty commonly, and then store and import from a local file. And so when I'm trying to refactor, it gets very hard. It's an understatement, but it gets very hard.
Yep. And you're left wondering, is this a module in the current directory or wherever they appended to, or is this some normal place on Python path? Well, that could be very confusing. Let's go ahead and move on to the next round. Round 2, how do we loop? In this example, we're using NumPy, so we're loading some NumPy data. So X is undeniably a NumPy ND array. And then we iterate it. Is this really that bad?
I think it would be that bad. You could probably use something like NumPy to optimize the loop initially, but if for some reason you don't care about the actual separation between the rows, you can merge that into a single for loop, where you put a generator expression in that first for loop of something like for x in row for row and xs in that single line, and that should be able to loop over everything as if it was a single list, flattening it essentially.
Mm-hmm. Anyone else on the panel? Thoughts?
Yeah, I think I was also meaning to mention, I think it also depends, right? I mean, if we're already using a NumPy array, in this case, for example, and let's say that we're trying to do a multiplication between two matrices. I mean, sure, it's not incorrect necessarily to loop around these elements within these arrays and be able to compute the operation from scratch. But I mean, also being aware that tools already exist and that we have access to them, and that potentially we can increase the performance of our code by quite a lot by using these predefined functions. That will be the way to go. So I think my question will be more of is this code just a prototype that I just need right away, or is it going straight to production? Because I think that then the answer to this question kind of like is different, right?
Yeah, I totally agree, Tanny. I think depending on what you're trying to do to every value in X, if it's a true UDF, that's a user-defined function, then you might not be able to get away from iterating at the Python level. But what NumPy is, of course, known for is that you can push a lot of computation into much lower level looping structure into C, C++, or Fortran, whatever your back is written in. But if we're doing something very simple, like I want to add 5 or I want to add 2 arrays together, then I should just let NumPy handle that because it's going to have much better speed in terms of execution. Now, is this really that bad? In my opinion, I wouldn't say this is the end of the world, but you could very well get better performance out of your program if you relied more heavily on NumPy's operations instead of doing some manual looping. Any other thoughts from our panelists?
I can quickly add that I've experienced some situations where you need to do, like you could write a NumPy operation as a tensor, like as a tensor operation in like Einstein summation notation, right? There's NumPy eig something, not eig, but you know what I mean. I forget what it is.
Yeah, there's einsum.
Yeah, einsum, yeah. And you can literally write out, and then it'll blow up your computer with memory, right? So sometimes you do need to use loops. I'm usually of the opinion that if you're coding for loops in Python, you're probably doing it wrong, unless it's some simple loop over like directories or something. For any numerical operation, like Tanny said, there are better ways. But there are some situations where maybe you're dealing with operations that you need to do a for loop over to fit in memory. And of course, there are other programs for this like Dask. But if you want to keep it in sort of if we're going to, NumPy is not part of the standard library, but I mean, it might as well be, right? So if you want to keep it very Pythonic, then that would be one reason you could use for loops.
Yeah, I think, the memory use is a very valid argument here since NumPy will implicitly perform broadcasting, which depending on your use of it can actually cause no increase in memory consumption, but it can also, however many times you're broadcasting, it can result in that much larger size of array if you concretize that result. But thank you for that additional information, Matt. Let's go ahead and jump into round 3. How do we Python? Do you have multiple versions of Python installed? If so, is it just Python 2 on your computer and Python 3? Is this really that bad?
I'm indifferent a little bit.
Feels neutral?
There's too many variables here to kind of really say whether it's good or bad. The script could have a shebang at the very top that indicates the Python version to pick up, so you don't necessarily need to do anything other than call it as an executable. Maybe the script itself didn't get migrated to Python 3 because, collaborations are very slow to move from Python 2 to Python 3. Even in a collaboration of 6,000 people that I work with, most of the code is still in Python 2, unfortunately. And just even getting people to Python 3.7 2 years ago, and now I have to force them all to 3.8 because 3.7 already died. I'm indifferent.
Indifferent. So not the end of the world, but, at some point we're going to keep moving forward. Any other thoughts from our panel? If not, I have a few thoughts and then we'll move on to our final round here. Python version management and environment management are an incredibly complex topic. For Python version management, you have a lot of different tools, including things like Anaconda, which is a little bit of version and environment management. And you have tools like PyEnv, you have tools like RTX, which all allow you to install multiple side-by-side installations of Python. And so I would say, as long as you're using something to manage which Python version you're specifically using, because in my opinion, if I saw something on the command line Python 2, I would say, well, it's got to be 2.7.11, right? It's got to be the latest version of 2. Well, it could be, it could require an earlier version of 2. And so even with typing Python 2 at the command line, I'm not being as explicit as I could be. So that's just my personal take on this, is there might be better ways to side-by-side install versions of Python and manage those than just having an alias on your command line or your shell. Let's jump into our final round. How do we serialize? Now, if you're not super familiar with the pickle module, this is all about serializing data in Python. So this will serialize all of your base types. You can drop them into a .pickle file, and you can load things like dictionaries or namespaces from a binary file format that doesn't need to be reinterpreted like something like JSON would be. So, seeing this, is dumping things to pickle really that bad?
Is this in Python 3 or Python 2?
I'd say the ambiguity might hint that it could be not the best thing.
I think this one also depends on the context. If this is in a Dask worker that's sending data to another Dask worker to be used immediately, and they trust each other, as is usually the case with Dask workers together, then great. If you're planning on emailing this to someone or opening it up next week, maybe not.
Well, the reason I asked if it's Python 2 or Python 3, if this was Python 2, I would say use cpickle instead of pickle just because that's going to be a little bit faster and give you smaller data sizes. If this was Python 3, I would say use pathlib instead of actually calling open file name and just dumping it that way using the write binary function on the path object. But then again, kind of following up on Dan's point, if I was going to work with NumPy data, then perhaps I would use a memory mapped file because that's easier for NumPy to share buffers when you're talking about multi-threading or multi-processing or something like that, rather than pickle.
Absolutely. There's a lot of reasons to use pickle and to not use pickle. And I think Dan's example is a great one of when we want to use Pickle. Typically, the rule of thumb is if all you're doing is moving data just from one place to another, and you're going to be working with it in the exact same way with the exact same version of Python, you're not going to have any issues. If you're relying on Pickle for the long-term storage of data, well, you better write down the Pickle serialization version that was being used, or the protocol version that was being used, as well as the exact version of Python that you are using, because these things do change over time. So Pickle files written 10 years ago aren't parsable by the modern Pickle standard, so you have to figure out which standard you were using at the time in order to actually unload that Pickle file. Additionally, if you want to share or send Pickle files to other people, that's fine, but do know that Pickle files can execute arbitrary code. And so if you want to actually load in a Pickle file, you will be executing code that they have written. And that could give someone with more malicious intent some not great things to do on your computer. But that does take us to the end of our fourth and final round of our coding activity. I want to thank our panelists for doing such a fantastic job of driving some discussion for today. With that being said, Giordon, I would love to turn things over to you so that you can share with us the prepared remarks that you have.
And so what I wanted to kind of talk about today is one of the many different software packages that I work on. I mean, there's quite a few that I could have talked about for today, but I wanted to talk about one that we recently published a paper on, and this package is called Mapide. And the pi in here does not stand for Python, although it's kind of a fun coincidence that I can stick a pi in there. So first, just to give a brief about me, which you've already heard, I got my bachelor's in physics at Caltech, but at the time I was working on the Laser Interferometer Gravitational Observatory. There is where I picked up a lot of my Haskell and Perl wisdom. And although I've quickly forgotten most of the Haskell at this point, I still kept around a lot of my Perl knowledge. Since then, when I went over to UC Chicago to do my PhD there, I worked and I am still currently working on a high-energy physics particle physics experiment located in Switzerland called ATLAS. And I got my PhD on this, searching for new physics beyond the Standard Model, as well as instrumentation upgrades of the large billion-dollar detector that we have there. And currently, I'm actually here at UC Santa Cruz, called Skip, and I'm a postdoc here since 2018. I'm still doing all this sort of the same stuff that I've done as a grad student, but just more of it. So I tend to be stretched thin. I do a lot of physics analysis work. I do a lot of hardware development work, hardware testing for future instrumentation upgrade, as well as software development, outreach, and educational classes trying to teach other people how to use software such as Git or GitLab CI/CD pipeline, or just even using Python. But I also, because this is theory and I wanted to give a brief overview of some of where my programming knowledge comes from. The funny thing that I like to joke about is that I've never actually had any sort of official programming course, or not even sort of like a training school in any way. All of this I've just kind of picked up over the years from kind of breaking things and then trying to learn how to unbreak it. When I was about 10 years old, I started with ActionScript because I thought it was fun to play around with Flash. And then that led me into HTML4 at the time, CSS2, and JavaScript. And I actually ended up contributing to Mood Tools, which on some level was kind of what inspired jQuery, depending on who you ask. And then when I did high school, I did a lot of Ruby and PHP. And I actually went around to see if I could still find my old PHP post in the PHP Freaks forum. And turns out they're all still there. So I have no shame, so I don't feel embarrassed. So you can feel free to look at my old post and see everything I've talked about with PHP. But now, at this point in my life as a postdoc, I do a lot more with Python, Docker, containers, C++, Bash, and continuous integration and continuous development, as well as Python binding. I put that in there because it is kind of Python, but it's kind of the merging of both Python and C++. And it's always a fun little thing to do. So for today, what I want to talk about is what MAPIDE is. So the way that I wanted to kind of approach it was to sort of motivate this from a particle physics perspective, what we actually managed to do with this, and then move on to the actual technical details of it. So I'll talk a little bit about what we do in high energy physics. For those of you who are not super familiar with it, what the typical workflow looks like when we have a published analysis, what it means to have the analysis preserved in some way or form, to have that data available publicly for people outside of the experimental collaboration to access, how to recycle that data, meaning both to reuse it, reproduce the results, because that's good science, but then also do what we call a reinterpretation, meaning that we come up with some new ideas for the existing data and try to do a reanalysis, a reinterpretation, and see if we have any new insights from that. And then after talking about all of that, I'll talk about how MAPIDE fits into all of this, the actual technical details of MAPIDE, and how to implement custom workflows with this. But I want to make sure that everybody has enough time to go through these slides, so we're going to go ahead and get started. I'm only flashing this slide very briefly. There's a lot of glossary terms that I'll mention here. I'm not going to mention any of these tools by name. I'm just going to mention sort of the role that the tool has in the ecosystem. But you can feel free to read this other paper that we published about 2 or 3 years ago that has kind of details of this entire ecosystem that we have in high energy physics. And honestly, it's a little bit chaotic, it's a little bit messy, but this is what we have. So I work on the ATLAS experiment, which is one of the 4 major experiments at CERN. CERN is a French acronym, but it stands for the European Organization of Nuclear Research that you see at the top right. And so at CERN, there are multiple experiments. One of those experiments is more focused on particle physics, and this requires the development of a very large collider called the LHC, the Large Hadron Collider. This is effectively a 27-kilometer ring buried about 100 meters below the mountainous terrain between Switzerland and France here, as you can see on the border. And ATLAS is one of these 4 experiments. There's also CMS, LHCb, and ELISE. So, what do we mean when we talk about these particle physics experiments? Typically, we have what we call a fence. And what you see here is sort of a cartoon diagram of the cylindrical detector that we have that detects particles that collide in the Large Hadron Collider. And normally, if we could collide 2 protons head-on almost perfectly, like an elastic collision, then our job would be kind of done. It would be much easier, but this is already difficult. Protons are very small. So what we tend to do as physicists is a little bit cheating, maybe a little bit lazy, is we just get a whole bunch of protons, 2 separate bunches, billions of protons in each bunch, and just kind of smash them at each other and hope for the best. But doing this is, there's a little bit of a drawback here. The drawback is to actually do this and to actually simulate these processes requires a lot of computing power, requires a lot of specialized software that knows how to handle all the different permutations and combinations and handles these sort of collisions and energy that distributes here. And it's very hard to do this, and it's very hard to model this correctly. And there's always a lot of work to improve the state-of-the-art modeling software that we have, as well as the state-of-the-art simulations that we have. But then on top of actually just simulating the physics, then we need to sort of feed it through our simulation of the detector, meaning our best understanding of how the detector itself is designed, where the material exists, whether we have, lead in this particular region or copper in this particular region, and knowing how all of these different particles interact with all of these different materials. And so we have to have, on top of having a particle physics simulation, we also have to have a detector simulation at the same time. And all of these individual pieces of software exist, and there's a lot of work in this area. So now that we have these individual pieces of software, we can collect all of the data at the Large Hadron Collider. What I wanted to point out really is that at LHC, for the LHC experiment, we measure our data set in a unit called inverse from turbines, which for the most part is just an inverse probability. And the point of this is that if we know the probability of looking for some sort of particle physics, such as say the probability of finding a W boson, we can multiply that probability by the inverse probability of the data set we have to determine the number of W bosons we expect to see total. It's just a convenient way of measuring this data set. At this date, we have about 20 more years of LHC or HL-LHC physics. HL-LHC is sort of the next generation of the Large Hadron Collider. If you look on the left-hand side, each of these square blocks here is kind of a play on the Wordle game that kind of took the nation by storm during COVID. But each of these boxes here, for the first recording period that we had at the LHC, was just a single box of data. The next recording period that we had from 2015 to 2018 is 5 more boxes. The current recording period that we have now, which we expect to end around 2026 or so, will give us another 10 boxes. But we still have about 50 more boxes of data to collect here. So we're not even talking about, 10% of the data collected over the lifetime of these experiments. And we have about 90 petabytes per year of data to collect. So this is kind of a large scale thing that we're talking about here. And the other thing I wanted to mention is that CERN has announced a sort of open data policy where 5 years after the period of recording data has ended, we publish all of the collision data and make it public for everybody to use. And so that gives us motivation to not only make sure that the analyses we do internally within these collaborations are done in a timely manner, and that they're reproducible, but that we make sure that they're accessible for everybody. So why are we preserving in the first place? Well, there's a lot of reasons here, and I'm sure everybody in this room already knows the benefit of making sure that analyses are reproducible and preservable. But one of the ideas that I like is the sort of idea of having this be fair. And fair is about making sure that the data is accessible both for theorists and for experimentalists, making sure that we have a way to do reinterpretations when new models come up or when our simulation software improves, and then we can rerun and see the changes and how those changes impact data that we've already collected. And so this is kind of a large project that just goes beyond me and goes beyond all of us in trying to make sure that this all works. And it's part of the reason why this ecosystem is very large and chaotic, because there's so many different pieces that we have to deal with. So I wanted to talk a little bit about what I mean by this analysis data being public. So in high energy physics, most of the analysis data that we publish is on a website called HEP Data. And you can see a screenshot here at the top right of what this HEP data looks like, and there's a link here at the top. I'm happy to share the link to my slides at the end of the day after this talk so people can go through these slides in their own time. But HEP data, for the most part, will contain digitized versions of the histograms and plots that we make in an analysis. And what I mean by a digitized version is it's essentially a lookup table in YAML, JSON, or root formats. It also will include public probability models, which are serialized typically in JSON, as well as different contours of the statistical sensitivity of the analysis, and lots of other numbers that are useful for theorists or anybody who needs to look at the analysis. The other thing that also gets published here is sort of an analysis description language. In the ATLAS experiment, we've opted to use C++ with a package called Simple Analysis, and I provided a link here for that. This simple analysis framework allows us to run the analysis at the sort of simulation level, meaning that the sort of events that we produce at the simulation level can then instantly be analyzed, and the selections are serialized in pre-compiled C++ code that are also available in Docker images provided by the collaboration. So, let's talk about MAPI very briefly. So as I've kind of already mentioned here, the problem here is that the HAP software ecosystem has lots of toolkits with lots of opinions, formats, and configurations. MAPI here is a highly configurable pipelining framework for allowing us to reproduce, reuse, and recycle these analyses using the public analysis data. It's an attempt to harmonize all of these different tools such as Magra, Pythia, DAWs, which are the three big ones in this ecosystem, and that's where we got the name from. But these are just the most common simulation toolkits that exist, and we try to harmonize them because each and every single different toolkit that we have, there's over 50, have different ways of configurations, different schemas, different inputs, different output formats, and this is very hard for somebody who's new, such as a student, or just even a new postdoc or a new grad student to particle physics, just to get started. And so this was a way to try to harmonize all this and make it more approachable. And it has what I would consider not necessarily super lightweight, but it's relatively lightweight. It only requires that you have Python and some sort of OCI runtime, open container infrastructure runtime, such as Docker, Singularity, or Aptainer. So I've already mentioned all of this here, but just to remind you, analysis have public data on HEP data. We have MAPI'd. So the first step here is to do a reproduction of existing results to make sure that everything looks good, and maybe do some tuning with our black box to match the experimental collaboration black box of their toolkits. And then once we make sure that we can reproduce the results, we can then come up with some new idea and do a reinterpretation. So what does this actually mean? So when I talk about tuning to do a reproduction, what I mean here is that both the experiment and what we have in MAPI have some toolkit that they've chosen for event generation with some sort of configuration. Depending on the analysis, the configuration of that event generation is not necessarily well documented. That may be on purpose, that may not be. But with MAPI, we know how we're doing our event generation. And so we're not going to necessarily tune this as much. However, detector simulation is the big one. Experimental collaborations, for them, their detector simulation configuration is kind of their bread and butter. That's not something that's ever going to be released publicly. That's something that allows experimental collaborators to be motivated to get this done, or to do analyses, or want to be part of the collaboration, because that's sort of the buy-in that you get. That's sort of the secret sauce that you get when you join the collaboration. But that's not necessarily great for theorists on some level. So what we need to do is look at the public data and just run through both toolkits. The experiment's already published everything, which you can see here as the light purple box, this public data on the right-hand side. We just do the same thing with MAPI. We kind of turn the crank and see what comes out. And we say, it's kind of similar, but not quite. So we make comparisons between what's been published, what we got out of MAPI, and then we just kind of tune the configuration of our detector simulation and get a tune config for that particular experiment. Then we run it again, and we get something that's close enough for our purposes, and that's a reproduction. So what does that actually look like? So on the left-hand side, we have three different lines that you're going to see here. The blue dots are what the experiment published. The blue line is the tuned version of the MAPI output. And the orange line here is the default configuration of that same detector simulation. And as you can see here, tuning is very important in order to be able to reproduce the results of the experimental collaborations analysis. And so the point that I'm making here on this slide is tuning is important and it works. So now that once we've done reproduction, we can do a reinterpretation. So an experimental collaboration might look at some sort of theory or model which have some sort of different particles in play, which you see here on the left-hand side. And then I would come up with some new models, maybe adding additional particles that I think might be worthwhile to look at as well in this particular model. and see what comes out of this data. And the question I ask really is whether these models or theories that I come up with give me any new insights with the existing data that's been published. And this is what it would look like when I run through MAPI, which gives us plots that look like these. And the blue dots here are the sensitivity of the existing experimental analysis. And then the darker colored boxes are the regions where we have better sensitivity with the new theory that I just ran through MAPI. And I'm able to come up with some new insights here and go, interestingly enough, that these new particles that I came up with are giving me some additional sensitivity that I did not otherwise expect from this particular analysis. This is something that I can feed back to the experimental collaboration and say, this is a good idea that you should look at for something that for your run-through iteration of your data recording. Maybe do a full-blown analysis with your internal detector simulation and see if we can confirm what I've got with my sort of ballpark reinterpretation here. So that was sort of the motivation of the paper side of things. For the next, I want to say 10 minutes or so, I want to go through some of the technical details of how this all works, just to kind of flash some code here and some novel ideas that I think are novel with this code that we've written up here. So you see here the sort of high-level overview with all these different toolkits, all these different configurations which you see on the left-hand side, and they all have to kind of pipeline and feed into each other in different ways with different formats for inputs and outputs. And MAPI, what we have out of the box from MAPI, stitches all of this together in a consistent, unified way for you so that you can kind of steer all of this with a TOML configuration file, which is very user-friendly. So under the hood, this is pip installable. This also exists on Conda Forge for those of you who like to use Conda. I personally don't use Conda, but a lot of people tend to use Conda, so I try to make sure that this was available on Conda as well. You also need to have some sort of container runtime, such as Docker Singularity Apptainer, because the Python code will be steering those images. And again, the configuration is TOML. And you might be asking Jordan, why not use an existing workflow language? And I thought about this and I thought I could. Part of me didn't want to have to go through the sort of headache of learning all the little details of that workflow language, but I tried to use a couple of them and I found most of them were a little bit too heavy for my liking and required a lot of sort of a steep learning curve when I'm trying to induct a new student in particle physics and get them introduced to sort of all the different toolkits that we have and actually doing physics. Having them learn a workflow language just to get started was not the greatest. And so this is sort of why we developed MAPI. So the TOML configuration for MAPI looks like this. This is just a snippet. It's not a fully complete snippet, but the TOML configuration allows us to split up different sections, and each section refers to whether you have, say, a base configuration more related to MAPI itself, then also sections that are configurations for all of the different toolkits that we might depend on, such as, MACRAF or Pythia, which are event generation or event simulation frameworks that we have. You can have configurations such as a top-level folder on where to store these outputs. We also use Ginger 2 templating in order to allow us to automatically generate or have dynamically generated names for output folders, such as perhaps when we do a grid of theory models here in order to kind of sample across our base space, we want to be able to have a different output for each different mass that we're trying to generate, and so that's where Ginger 2 templating comes into play and makes it beneficial. And then there's also additional things here, but once you have your TOML configuration, with MAPI, you just call MAPI run user.toml, and it will just do your entire pipeline, and that's pretty much it. The benefit here is that, yes, it is a black box, but it is a black box that makes it easier for a student to actually just get started and look at results and get an idea and tune or tweak individual pieces of it without having to figure out how to tie those pieces together. which is really honestly the hardest part of this chaotic ecosystem that we have. It's a good chaotic ecosystem, but it's still chaotic for someone who's new to it. The other thing that we could do as well, and I'm just flashing this here, is that instead of providing a path that exists on disk to a configuration file that you want to pass into MagGraph, for example, we also provide the ability for you to generate this on the fly using the feature of Tama, which is allowing for multi-line strings, which I find really useful as well to generate these configurations on the fly. So some of the other features that I want to mention about Mapai very briefly. Mapai has this concept of what I call prefixes, which are sort of these global configurations or paths where other configuration files might exist. That's what we might call cards. And so you can see these prefixes, there's two different ways of accessing them. The accessible just sort of within Python as just function, where you can set the new path, and that will globally set the path for your current Python interpretation session. Or you can do this through a context manager, which will only set the path temporarily within that context. And there's a lot of handy configuration that's shipped with Mapai out of the box. There's just, for example, a tuned detector simulation that I was talking about that we had done for that analysis. We put that into the Mapai package, and that's shipped when you pip install or put it on Conda. That's shipped as additional data that Mapai knows where that data is. So you can ask Mapai what that data is. You can also do this from the command line, which you see at the top right-hand side. And you might get an idea of why I'm calling it prefix, because it's a path prefix. And then you can access the data files under that prefix as well. So I can ask for my prefix of where the cards are located when I pip install Mapai, and it will just tell me exactly where it is. In this case, at the top right, I installed in a virtual environment, so it handles it that way. Another thing I wanted to highlight is the Ginger 2 substitution, which I was kind of happy about, that this was a lot easier than I was expecting it to be. Ginger is really great about this. We come with, for all of those prefixes, we can insert those as substitutions in your Tama configuration. So no matter where you install Mapai, you're able to kind of dynamically inject those prefixes on the fly when you parse the Tama configuration file. So this way, this means you don't have to hardcode paths on some level, and it makes it a lot easier to have the same configuration file run not only locally on your computer, but also on the cloud or Kubernetes, or using DOS, or some sort of job queue that you might want to use at the same time. And so, again, there's not a lot here. This is sort of the function that we have from Mapai that allows it to kind of render the templates very quickly. What you also see here, this double asterisk variables, this is another benefit of the Ginger template substitution here, where we can substitute in variables from the same Tama configuration that you're also looking at as well. So I'm just going to quickly go back for a little bit to show you what I mean here. So if you look at this second line here where we have output, maybe I can kind of highlight this very briefly. You can see this double curly brace here where we reference MagGraph, masses, and slip. That means you can actually inject the value of mslip down here under the MagGraph.masses block. And that's done through this double asterisk variable that we have here. So this means not only do we have access to the prefixes, but you also have access to the actual values within the same configuration that you're parsing as well. The last thing that I wanted to mention about these sort of configuration parsing that I really, really like, and I was really proud of myself for this because it's a recursive function, is to handle inheritance. But this is only inheritance up to a maximum depth of 10, because I decided there's no way people are going to encode nested templates more than a depth of 10. I thought 10 was a reasonable limit. I didn't want it to recurse forever. But the idea here is that templates can inherit from other templates and override values in those templates. And this is useful because maybe you want to build a grid or say 100 different configurations, but those 100 configurations inherit from a common template that I wrote. and only change one value of it. This makes it much easier for me to kind of run over all those different configurations I wrote using the same base template. And then I have this configuration here that allows me to build up the configuration, merging in all the nested templates from the lowest in depth to the highest in depth, and then inject the substitutions at the very last level. And there's a lot of details here. We can sit, if you're curious about how this works, we can sit down and I can show you more examples. But I wanted to show you a very simple example that I just kind of came up with for this talk. Imagine that we have two configuration files. We have what I call parent.toml. Parent.toml has a base template of defaults.toml, which is shipped with Mapide. And then I created a child.toml here, and that child.toml decides to change the name of or change the configuration of the MacGraph card that I would like to use. And so when I parse parent.toml, which you can see here on the right-hand side, I parse it. It tells me that the base output here is going to be charginos underscore 500, because as you can see here, in parent.toml, the ginger substitution is going to be charginos underscore 500. If I didn't do a lazy evaluation of this when I did it for the child.toml, I would still have the same output name, which isn't great. But having a lazily evaluated ginger substitution here means that when I parse child.toml, because I've changed the name of the MacGraph process card that I'm using, I now have the output being charginos underscore modified underscore 500. And so that's an example of what I mean by the lazy evaluation. All those template configurations get merged into a single configuration, and then I evaluate the substitution afterwards. This simplifies my inheritance so much more, and is easy to make clear. And this was a feature that I was sorely missing from all these other workflow languages that I was looking at. And then the final thing that I'll mention before I wrap this up is you can use all of this in Python to implement your own configuration with your own tool. This isn't necessarily specific. Nothing here about Mapide per se for the utilities that I mentioned here are specific for the parsing, for the template substitution, for the inheritance. This allows us to take common configuration files that you come up with and inject this with your own Docker images, with your own workflow and your own Python code, and still use pieces of Mapide to do the parsing and inheritance for you and get that sort of power, but you're not necessarily tied to the HEP ecosystem on some level. There are some other technical bits that I'm just going to flash here. The last thing I wanted to mention is what we have. It's called Mapide 2e, which you see a screenshot here up on the right-hand side. A 2e standing for Textual User Interface. Maybe you're familiar with textual, maybe you're not. Textual comes from the same group of people who made Rich. And Rich is fantastic for making pretty things in your terminal. And then textual allows you to build these sort of GUI apps, but in your terminal, hence 2e. And Mapide ships with a 2e as well. So if you're not familiar with the command line, you can spin up the 2e and just kind of go through a graphical user interface in your terminal and go through these different options that you have here. And so that's sort of it for my talk, and this is sort of the summary that we have here. Mapide itself allows us to enable the sort of reduce, recycle workflow pipeline that we have in HEP. But I feel like it can be a more general toolkit to enable other workflows that you might have, more as a pedagogical tool that's easier to teach new students about something that you're trying to do. Maybe have Docker images of different toolkits that are hard to work with, or maybe you don't necessarily want to teach someone all the different fine-grained details of how to feed data in it or feed data out of it, and you can wrap that in Python and let that run it for you and just hand off a smaller sort of DSL, a domain-specific language, or a smaller set of config of things you want to be able to tune or tweak with that toolkit that you're talking about. But again, we have a paper published here. This is also submitted to SciPostVis that we're hoping to get published there. The repository for the papers here, the data that we use for the reinterpretation, the reproduction exists here. And of course, all of these links at the bottom here are on MAPI. We have documentation, it exists on PyPy, it exists on ContraForge. We have a DOI on Zenodo for preserving the code as well. Thank you for listening and sitting through my remarks. Admittedly, I went a little bit long, but I hope you enjoyed it.
Thank you so much, Giordon. That was a fantastic set of remarks, and I love the tool MapID. Now, I would like to open up just a few questions to our audience. So if you have questions, either enter them in the event chat or the Q&A widget. And Dan, I believe you had already entered a question, so I'll go ahead and let you ask that. Dan?
Yeah, sure. Looking at the config files, I noticed that the results are stored in a directory. I was wondering how easy it would be to make MapID upload results, say, to an HTTP service.
Yes, that is something we could add in as well. For now, I just assume the file protocol. I mean, I will admit I'm pretty much one of two developers on this. My direct supervisor here also helped develop it, but I'm kind of the software expert for this. So I think it's a great idea if we could write directly to HTTP. I just wouldn't know what that would look like, but if you have ideas, feel free to open up an issue and we can flesh that out and make it supported as well.
That's a great answer. I think files are a very sensible place to start. Should I ask my second question, Cameron, or are there others coming?
Yeah, go ahead and ask your second question, Dan.
Okay. We do encounter many workflow managers, as you mentioned. Can you say a little more about what kinds of tasks MapID focuses on in order to achieve simplicity and a fast learning curve? Where does it really shine? And conversely, what shouldn't I try to use it for?
Well, so there's two different pieces of MapID. I guess what you're asking about is the more general, non-HEP specific part of it, which is what I envision MapID to be used for outside of the HEP domain. Is that correct?
Yes.
Okay, so the way that I think about this is some of the workflow languages that I've looked at, like say SnakeMake or, Yadage, my frustration with them is that maybe they were on some level designed for a large cloud or Kubernetes first, rather than sort of, I have my little machine here and I want to be able to run something very quickly or run this workflow very quickly, but then also allow me to kind of tie that in with existing queuing, blocking, ways of distributing that job as well. I don't know what the phrase is for that sort of ecosystem. I think of like Dask and Condor and all of these other additional tools that already exist. And so I want to make sure that MapID is used at first for things that are containerized and can be written very briefly. So if we look, for example, at this custom usage, what you see here is that we have this sort of image that we specify. That image can be anywhere, and we don't make any assumptions about permissions for accessing that image, like authentication or authorization. That's more like host machine configuration kind of thing. And then you can specify the command here. And we have the sort of container class that we built up. And I think I can flash the container class a little bit here. This was inspired by CI build wheel, and this container class is sort of another sort of magic piece that allows anyone to kind of run container images from Python without having to think about some of the details of how to deal with, the standard input, standard output, how to deal with where the logs go, additional options dealing with the current working directory, dealing with mounds. All of that gets wrapped up into this container class. So then I can basically write a piece of code like this for any sort of Docker image I want to run or mount in any particular way, define my own sort of configuration I'd like to feed into this, then say, here's the sort of schema of configuration you can use with this piece of Python code. You can run this workflow that I've come up with. But it's very, let's go with very non-opinionated, which I think some of the other workflow languages might be more opinionated about.
Mm-hmm. Thanks.
Is that clear enough? I mean, I'm doing a terrible job of explaining it.
No, I don't agree. I think you did a fine job. Yeah, that covers my question.
Excellent. And if there are no other questions, we can go ahead and adjourn for the day. Thank you all so much for joining. And very importantly, I want to extend a huge thank you to Mindy for her fantastic interpreting and to Giordon for not only sharing his remarks with us today, but also for working on such a fantastic domain-specific reproducible workflow tool that simplifies the lives of researchers. I also want to thank you all, our audience, for joining us this month. If you're not already signed up for our newsletter, make sure that you subscribe. The subscription link can be found on our website. That's meetup.doepy.org. Or if you don't like receiving one email per month, make sure that you keep a regular eye on the website for information about our upcoming exchange next month, as we'll be joined by Logan Kilpatrick, who works at OpenAI and helps developers create tools around ChatGPT API and plugins. Logan additionally serves on the board of directors for NumFocus, so you know that he'll have his finger on the pulse with all your favorite tools. Thank you all again for joining, and I will see you all next time.